My name's Nicolai Plum, and I'm going to be talking about Datastore axes, how to choose the scalability direction that you will need for the system that will be storing your data. So where did this talk come from? Well, initially it came from the fact that our developers get to design and build and operate their own product. So, we said to the developers, you have autonomy to design or build your own product. But you must tell the database engineers, people like me, how their product will grow and how its database needs will change. The developers said, help. They have responsibility for building their own product, but they don't know how to do it. They don't know what they need. And they go, I can't predict the future. I can't answer this question. Meanwhile, the database engineers would like to have our product be well defined. The service that we provide should be a well-defined product with clearly defined capabilities and also clearly defined compromises. We cannot build something that is good in all directions. It is difficult to change the laws of physics. So in this talk, I'm going to be talking about a data store, which in this case I'm using to mean a system which stores and retrieves data. In this talk, small data. Each individual data item is not very big, but they could be very numerous. MySQL, stuffing things in Cassandra, that sort of thing, not Hadoop. It's reliable and it's durable. And, it may have multiple components inside the black box, data servers, routers and proxies, orchestration and all that sort of thing. So that's the sort of data store that I'm talking about. Now, if you have a small system, everything is fine. New products, which don't have a lot of users and a lot of customers, don't have performance and scalability issues. There is no need for compromises in the design, in the storage. And, 70 years of previous computer industry development has kind of solved the problems for you. They've made computers that are good enough to run your small product. But then your system grows large, and nothing is fine. You have performance problems. You have scalability problems, always. You have to have design compromises because your technology cannot do everything you would like it to do all at the same time. Now, established products and services are large systems and they have issues, but they also have users and they also have revenue impact. So now not only do you have scalability issues, but you actually have to solve them because money depends on this, or science depends on this, or whatever your enterprise is doing depends on this. These systems obviously live in the real world. So you have to think about how you're going to relate the system that you're building, especially a data store, a piece of infrastructure, to an application product, but ultimately to the real world, both the real world of the users who are using this product that's using your database service, but also the real world of the hardware. Unless you build your own hardware, and I do mean build your own memory chips and so on, you'll be getting it from someone else. So product users come from the real world. So you can ask developers and product managers and scientists and so on, what's driving their application? You can also ask the accountants, not the accountants that do payments in and out every day, but the people who look further ahead, the management accountants, the financial planning department and so on. If you can connect what is going on in the applications that you're supporting and the industry that you're working in with what the accountants say, then at this point you don't have to do your own planning. You can just ask the accountants, how many customers are we having? I know what it takes to support one customer. So accountants can be your friend, even if you may not be accustomed to this idea. So you also need perhaps to do your own business and industry research. I mean, this is sort of a layering violation in some ways. If you think that you do technology and somebody else does business, then maybe you shouldn't be reaching across the layers of business. But it will save you to know kind of where your business is going or how fast it's growing. Especially in some cases, the people using your service may not know that what they're doing is about to be very popular, and you can help them out. It is useful to know the bigger picture. So obviously, keep up your contacts and don't be isolated in your little database world. Ultimately, you're looking for kind of fundamental controlling parameters and the fundamental constraints of what is going on. If you are providing a service to everybody in the world, your user base will be growing by about the population of the world. But if you're providing it to some sector of people that is growing very, very quickly, then you might have much faster growth. But you also need to relate to the real world of technology, the technology that comes from the real world and that is outside your control. You don't have control of CPU speeds and that sort of thing. So you need to know your technology capabilities, the hardware metrics, the performance, characteristics that are available to you. There are many other very good talks at this conference about that sort of thing. Benchmarks, testing, learning from others. Using your knowledge and your experience, you have probably seen a developer do this before. If you provide service to a lot of developers, the developer may not have done this before, so you may be knowing more than they do. On the other hand, they may have done this before and you may not, so perhaps she knows more than you do. Again, look for the fundamentals. Trying to understand everything is very difficult, but if you understand what is actually truly important, you can ignore the rest. So here's a really simple example. If you start off with an application that's got a very few users, not very busy, your servers will cope just fine. But as your application becomes more and more popular and application CPU demand or other resource demand grows faster than server demand, eventually you'll come to the crossover point, and after that you will be eternally in the world of large systems with scalability issues, with performance problems, with compromises. Now I'm saying CPU, but what about network? Networks are really fast these days. They're essentially limited by CPU, the speed that you can marshal and unmarshal the data, to stuff the data into the buffers, out of the buffers, over the network, through the network switch, etc., etc. And storage, again, storage these days is really fast. Solid state storage is fast, network storage is fast, usually because it's a bunch of solid state disk at the other end of a 10 gigabit network, which is fast. Latency becomes an issue, but really that's more for the developers to deal with, because latency is always with us. The laws of physics and delay are always with us. It's difficult to speed up light. So when you're thinking about the fundamentals of all this, think about constraints as well. The theory of constraints was mentioned earlier in another talk. And find the constraints on scalability. What are the limiting factors here? What is the thing that is going to crack first in your systems? The fundamental controlling parameters don't change very often, but you still have to check them. An example from hoteliering. A while ago, we wanted to know how many hotels are there in the world. This is actually a really hard question to answer. So a bunch of people did quite a lot of research, and they came up with a number in the past that they said there are about 500,000 hotels in the world, multi-room properties like this one we're standing in right now. That was a good number to have. So we built some systems, and we assumed that there would be about maximum 500,000 things listed in our catalogue of hotels you could stay in. But then the world changed. People started to rent out their homes. People started going holiday villas and that sort of thing. And we wanted to sell holiday villas and holiday homes and rental accommodations and caravans and all sorts of other stuff. And so the fundamental parameter of how many properties do we have exploded. And now we have millions. Will we ever have billions? Probably not, because that would mean renting out everyone's house. And I know that's a business plan of some other parts of this industry, but it's not really our business plan to rent out everybody's home. So once you've worked out the fundamental controlling parameters, focus on them, and then also tell your developers this, if you're working with developers on this, so that they can understand that they can, in fact, predict the future. But because ultimately, we're all of us in this together. Datastore and application scalability problems are connected. And core infrastructure, database, production engineering, whatever you call them, teams, they may have more experience of this and more knowledge of this, but yet they must also educate developers and also delegate to them. The reason why we're doing this in the first place is so that a small bunch of database engineers are not the limiting factor, the constraint, on the growth of the business. Instead, the limitation is how skilled all the people in the business are. But also, really, in the end, we all get paid from the same enterprise revenues. If this product fails because of the database, we don't get paid. And if this product fails because the developers couldn't manage to develop, we also don't get paid. So if you see trouble coming, it does help to understand the wider issue, even if that's not strictly your problem. In my team, we provide database services and so on. We essentially also provide an advisory service. If you have trouble, we will try to help you. And plenty of people make use of that. So, When you've got your systems that you're building and you're trying to analyze where the future is going to go, you can see that there are several directions that you might need your data store to scale up. This talk is mostly about working out what scaling you need, not exactly how to solve it, although we'll be giving some examples. Data size is the first one. Data grows bigger. But also schema growth. In this case, schema complexity. This also applies to NoSQL systems, because although they don't tend to have a schema, they do tend to have data organization. Either the application decides it, or it's a document store or something like that. So, first of all, data size. On the simple level of an SQL database, or even a NoSQL database, just replace rows with documents or whatever you want. More rows, more tables. Perhaps you have more tables even though you don't have any new data because you decided to partition your data in some way. And this sort of thing is caused by the obvious thing, business volume growth. More users, more people subscribe to your website, more people booked a hotel. You sequence the genome of more animals, whatever. But also by analytics. Data tends to cause data. So people produce data by analyzing the existing data. And the more data you have, the more interesting analytics people can do with it, and the more data scientists you can afford. And these people generate data like rabbits. So there's also logging, of course. All these transactions will each have logs. And then data retention. You'll be needing to keep this data. So as this product or this enterprise runs for some time, then you get compounded data from retained data from the past, from logging of the past, and analytics of all that data, and the current future data. So what effects does that have? You get problems like, in an SQL world, you can't do ad hoc queries anymore. If you didn't think of the question beforehand and put the right index in, it does not work. This changes from, it'll be a while before I get my answer, to I will never get my answer. I will never get my answer, not this week. People end up having to do things like split data across servers, which makes it harder to query. It means the client has to marshal the data. You end up trying to re-implement some sort of MapReduce setup, and it's slower. If you don't split up the data, then you end up with less processing power per unit data. One server, 1 terabyte. One server, 10 terabytes. It cannot be as fast. But then not only is your data growing, but typically also your schema is growing. It's becoming more complex. So you have more columns, more tables, but you also have more relations and more references between them. You have a lot more data model complexity, and because you have a more complex data model, you can do more complex queries. People do many multi-way joins. People add foreign key constraints. Foreign key constraints are a topic I could do a separate talk on, but you should generally just avoid them. And schema growth comes from other things than data growth. That's why it's orthogonal. Obviously from, more customers, but more product complexity, more analytics. People can make your schema more complicated if you didn't get any more customers by trying to build them a new product to sell the existing customer base. But also it grows because of developers. People have frameworks, ORMs, abstraction layers, that sort of thing that can make things massively more complex. And the effects are, your database or your data store begins to struggle. You need to spend more time tuning queries. You need to have more indexing overhead in time and in space. You also have more queries for each end user action. If you have a more complex schema, you need to query it more. And if you have more data, and it's more complex data, then you have more read queries. More queries on more rows, more rows retrieved from disk, more data to sort and send, which again is caused by, business growth, which is why you really want to relate to the real world, finding out where is this business growth coming from and how big is it going to be. And if the developers aren't doing this for you, you need to coach them into doing it so that they don't give you a nasty surprise later. Also, sometimes customer behavior changes. For example, when there's a recession on, e-commerce sites find people click around more before they buy. They're more careful with their money. So there's more hits to be served for each dollar of revenue obtained. But also, perhaps, the website could get new features. It could be more interactive. People at Google have told me that they certainly did have to re-engineer their systems a bit before they introduced the type as you search, because the query rate went up by several times. And read growth is disconnected from revenue, which can be a bit nasty. Like I said, people are browsing around more, but they're still buying the same amount. It causes all the strain that you might expect. More strain on server, IOPS, memory, cache, network traffic. Needs more scale out in some way. Read query scale out is often the easiest one to solve. And then there are write queries, which are usually harder. So we have more transactions, more logging, more audits, more analytics, more data pumps and ETL operations pumping data in and out. Not only business growth, but also things like curiosity, security, more regulation, more need to keep track of things, more requirements to log exactly what is going on, but also the richer customer experience, saved preferences, breadcrumbs. You've just looked at these things. I mean, just look at the front of Amazon.com and see the amount of data that's read and written every time for it to show you this personalized view. Booking.com is also heavily personalized just for you. Apart from clearly working your servers harder, because you're trying to write and update things, you get more contention, more locking, more stress on your data replication mechanism. So, having covered the four axes that we have, read rate, write rate, the data size, and the data complexity, let's move on to a few examples. So, first of all, a little bit of notation. We've got the axes, and then the blob just shows which way is this going to help us, or which way is it going to demand more from our system. Obviously, on the server side, it's what it can provide. Hopefully, these blobs will match up. So clearly, you can have better application coding. It would obviously clearly be nice if developers wrote better code. It would clearly also be nice if frameworks wrote better queries too. But there are things like not iterating on a database. Do not run a loop fetching the information for each product. Just fetch all the information for all the products at once. It's very easy for people to go from I have a simple product to I have a complex product, and I'll just repeat the simple operation many times. Someone has to go back and refactor this to a vector operation or to a set-based operation. You can do it in parallel, you can do it multi-threaded, you can do it asynchronously. It would be nice if the client code was just generally fast. We can see at the side there that this sort of thing, helps a lot with data growth, because if you're querying this data more efficiently, data growth will have less of an impact on you. From the server side, you can just simplify what you're going to support. It would obviously be nice if the developers used simple queries, because most relational data systems and some non-relational data systems, they have features that are fast and features that are slow. And the SQL standard is a very large standard, and many corners of it should not be used on any kind of serious production system. So you can say, I will not support complex joins. I will not support features that I know to be weak in this data store. No, you may not do complex subselects in MySQL on my database, because I know MySQL is not very good at these things. You will not have very complex data models with foreign key constraints. You will have good indexing. You can also discourage pointless server load. Don't get the database to sort for you. Sort on the client. This kind of thing is clearly a compromise with developers. You have to work out how much you are delivering to the developers that they can actually do their job, but not so much that you're finding it impossible to deliver a good level of service with this complexity. This helps good for, data growth and read queries and, even schema growth and so on. It doesn't help too much with write queries, because if you're doing complex write queries, you're truly doing it wrong. Like updates should be really simple. You can use caching. Most of the time, on a good day, this will make things faster, but really bad things can hide in the averages. You can have a very good service rate on a 90% cache hit rate, but is 10% really disappointed people, 10% bad performance acceptable to you? That really depends on your application. But most people do not like irregular performance. You can compress things. You can compress things in the application. Several people at Booking have written a very useful library called Serial, which is free and open source, which you can use to compress data on your server side and put it in your database or in your data store. You can compress in the database. MySQL has InnoDB page compression, and you can compress on the disk array in your storage controller. Some of these things have more overhead than others. Storage controller is basically free because that's the storage team's problem. Application compression is also kind of free because that's the developer's problem. Database compression is not free because that's my problem. You can compress across the network. Usually the network is fast enough, but if it's not, protocol compression can be a win. A lot of database access protocols are really chatty. They're very, very verbose. Just simply passing it through gzip, which MySQL will do and other databases will do, works very, very well. Clearly, this just helps you with data growth. That's what compression's for, really. And then you've got replication, more copies of your data. Replication covers a whole number of sins, or a whole number of different features you can do. So with MySQL, you can do replication in a hierarchy, several copies of your data, all of them read-only. If you have a cluster, you can put more nodes in your cluster, and you'll have more copies of your data just implicitly. If copy number is a question in your storage cluster, you can turn up the copy number. I mean, 3 is probably a good copy number if you want data preservation. You can turn it up to 10 or 50 or 100, and then you will get better performance because every node will have a copy of the data rather than just 1 or 2. So you'll never get redirected from node 1 to node 2 because node 2 is authoritative. This obviously causes more effort replicating data. If you turn that copy number up, every update takes more effort. So replicating your data is neutral at best and bad at worst. Depending on what kind of cluster you're using, you may need to separate read and write queries, but you should be doing that anyway. Your developers should be addressing the read and the write section separately. Some clusters claim you can write anywhere, but in practice, if you do write into both sides of the cluster, you get a lot of deadlock in the middle, and you should only write into one side of the cluster. You can write it, you can pick any point on the side of the cluster to write, but you should be reasonably consistent. MySQL group replications particularly strongly would like that. So simple replication, we've got one master and we've replaced it with a bunch of copies. Cluster databases, we've got this kind of benzene ring of database in the middle that just sits there. These are systems like MySQL group replication, Galera, Cassandra, etc. MySQL Cluster is an interesting hybrid creature. You've got a set of SQL nodes on the outside, and then you've got the NDB cluster layer in the middle that's organizing, putting all your data in the same place. MySQL Cluster is it's an old product. It's been around for quite a while. It has a bunch of interesting different design features. So cluster databases are not all created equal. For example, MySQL Cluster, it's very fast, it's very reliable, but the data size is a little bit restricted and so on. Cassandra has high read rate. It's reliable, not as reliable as MySQL Cluster, but pretty good. You can have huge data size, which is really handy, but it can only cope with very simple queries. It is a NoSQL store. It's nearly a key value store with secondary indexes. So you can see how, MySQL gets a bigger blob when it comes to data growth than Cassandra gets a bigger data blob than MySQL, but MySQL is much better for write queries. MySQL Cluster is really fast when it's up and running. So, apart from creating many copies of the data, you can also just split your data up. Just to get our terminology clear, split here is tables from one schema, each to separate schema. You can declare a maximum schema size. Beyond here, you will have to split. That's that's the service level that you've agreed. So you can move some tables out to a new schema. Hopefully you preserve locality of reference so that people can join up the same tables that they're accustomed to joining up. But it is a lot of work for developers. It's a lot of work for developers, but it will solve your scaling problem quite well from a database administration point of view. Again, terminology, just to make sure. When we talk about sharding data, we're talking about splitting the same table across several databases. Same schema, data in different places. Thank you. This is multiple data servers with the data distributed between them. If you do this in the application gets more complicated, and that causes developer work. Obviously, also, some queries will be much slower than others. If you have to cross between shard 1 and shard 2, the client has to make 2 queries, join things up. This is much slower than just asking the database to select your data for you. There are auto-sharders now available, Vitesse, Spider, some others. These have really great potential, but they still have a limited query subset because they cannot join everything up. They cannot do transactions arbitrarily. They usually limit your queries. They are much more complicated to operate than a single standalone database, but they are easier on developers. So again, this is something you have to compromise with on your developers, compromise with your developers, rather. So finally, I'd like to say an example of all this. So imagine that you're running a business. Possibly it might be a very large hotel reservation business, or it might be some other business, like, for example, something involving selling fabulous owls, if you work for Google. And so for recording transactions, like recording the core transaction data, the actual money spent, etc., the actual customer details, clearly you're going to be writing a lot of data. But it usually turns out you'll be reading quite a lot of data too, because you'll be needing to update this transaction as you deliver the service and as people pay you and as you deal with other things like invoicing and taxing and so on. And then you'll be reading from this as you service it, send them updates, answer their queries on the self-service web page and so on. And you will also need to store some amount of data. There will be some data growth here because you will want to keep those transaction records. So what kind of solutions might you like? Well, you could split the data. But that's going to be really hard on the developers because you're now going to be asking them to process a transaction across multiple tables in several places, and all those very difficult computer science PhD problems of transaction locking and distributed transactions is going to all fall on the developers. You could use an auto-sharder, perhaps. You could use MySQL Cluster. So if we have a quick look at the axes of scalability of an auto-sharder, we can see it's a reasonable match for this core transaction data. The schema's not too complicated. There's some data growth. There's some write queries. There's some read queries. It would probably work. Or you could use a cluster database like MySQL. Well, that's definitely got the read rate. It's definitely got the write rate. Data rate's probably okay too. So in the end, you can see that if you analyze the different directions that your application needs are likely to grow in by relating them to the real world and by relating them to the products and the users and the technologies that these things are built on, then you can take the capabilities of the system that you are delivering, how big can it grow, how many transactions can it do, what kind of read and write rate can it handle, how complex a data model can it handle, and you can try and match these up. And if they match up, you will have predicted the future, and you will have said that when someone says, I need to know what's happening in the future, you can say, here is roughly what is going to happen in the future. And then you can be happy, and you won't have any scalability issues and surprises in the future. I have time for a few more questions. Thank you. Like 2 minutes, I think. Go right ahead. I'll talk fast.
Hi. Oh, sorry. That was loud. Sorry, guys. You mentioned simplifying query support as one of the mechanisms to help. So how have you chosen to enforce that with your developers? Is it just via communication, or have you gotten fancy with any sort of stricter enforcement?
Things like foreign keys and so on, we just say, no, you can't have them. Because we have a way to moderate schema changes. So schema changes have to go through some tooling for compliance checks, and also there's self-service, but it's kind of assisted self-service with sanity checks. It says, no, you can't have a foreign key there. If people want to write really stupid queries with massive multi-way joins, what they tend to find is it goes slow, and then their product doesn't perform very well, and so it doesn't make so much money. And we A/B test how well products and changes do extremely well. So they generally find that it just doesn't work very well for them. However, if we reach the stage where we actually essentially have to stage an intervention and go and have a look at what is going on with the database, then we may perhaps give them some advice on how to improve the situation there. But that's more up to the developers, and we give them guidelines. We give them a lot of design freedom with guidelines. It's more guidance than control, if you see what I mean. Okay. Anyway, I'm very happy to answer any more questions later. I shall yield the desk.
Thanks, Nicolai.
Thank you.